Okay, good day to you all. My name is Mr. Patrick J. Mack, and I am the partner of Miss Alce for Chapter 9 Virtual Memory. As Miss Alce is the one to report about Part 1 of Chapter 9, starting from thrashing, I am the reporter, and I will be the one discussing the rest of the topics until the end of the chapter. So, first off, I would like to get back to the topic of steps in handling a page fault, because I believe that this is very essential in understanding the further topics. For first of all, why is there page fault? The operating system uh, intends to bring the degree of multi-programming higher. So this means that the number of processes stored in the random access memory must be more than one, so that the CPU can execute almost all the time. But the problem is, what if the CPU executes instruction in a page which is in the random access memory, but the next instruction is not in the random access memory, like this one. So what it does is it triggers a signal, a trap, to the operating system, and then it sends, or it suggests to the operating system that the page that includes the instruction to be executed by the CPU is not in the random access memory. This means that it's either in the logical address or in the hard disk drive. Now, if it is in the hard disk drive and it's not in the logical address, which is a part of the virtual memory together with the physical address, then it will get the page in the hard disk drive, put it in the logical address, and then from the logical address, it will bring itself to the physical memory or random access memory inside a free frame. And then the operating system will reset the page table, which is included in every process control block under each process, and then it will restart the instruction, just like what is indicated here in step 6, so that the CPU can execute the process at this time. So bear in mind, I would like to include this as a preliminary, that free frame is actually the name of the partition in the physical memory or random access memory, and page is actually the name of partition in the logical memory located in the hard disk drive, and file system is the name of the location of the file in the hard disk drive outside of the logical memory. By the way, logical memory and virtual memory are interchangeable. They are one and the same. A page table is included in every process control block of every process. So that's it for the preliminary. Okay, now let's move to thrashing. What is thrashing? Thrashing is actually an event performed by the operating system. As we all know, whenever a process lacks instructions in its process control block, it has to page fault so that the operating system can get the page that includes the instruction to the physical memory or random access memory, so that the instruction being processed by the processor can be restarted. The problem with this is the operating system has its own way of um, getting free frames from other processes in the physical memory or random access memory. And so, if the process that triggers the page fault gets enough free frames from other processes, because there is a decrease of number of free frames in the other processes, then those other processes eventually will trigger page fault. And if all the processes in the physical memory are triggering page faults, then the consequence of this for the processor is low CPU utilization, because CPU will be used for I/O bound instructions, for getting enough free frames, for getting pages from the hard disk drive, instead of processing uh, CPU bound instructions. So it says here, if a process does not have enough pages, the page fault rate is very high. So what the operating system does is it page faults to get a page. Now, that page gotten from the physical, or rather from the logical memory, will be replaced in the existing frame. Now, that existing frame has to be taken from another process. This is what the book calls global page replacement algorithm. But quickly, the replaced frame is needed back. And so, this leads to low CPU utilization, and operating system always thinks that it has to increase the degree of multiprogramming or add up more processes to the random access memory. And so, the operating system will get another process added up to the physical memory or random access memory. And this is what happens when the event thrashing is done. No, thrashing is a process. No, busy swapping pages in and out. Let's move to the next slide. This is actually a visualization of collected data, given that the x-axis is the degree of multiprogramming and the y-axis is about CPU utilization. So if you consider this one, at this part right here, there is an increase of degree of multiprogramming. This means that many processes are stored in the random access memory in order to be executed by the processor. And as the degree of multiprogramming increases, there is a direct proportionality that the CPU utilization also increases. Why? Because if you increase the number of processes, then the CPU has very so much processes to be executed. Now, at this point right here, there is a decrease of CPU utilization as the degree of multiprogramming increases. Why? Because there will come a time when the processes will lack frames or pages necessary for them to execute, and so the degree of multiprogramming increases, but the CPU utilization decreases because the CPU will now be used for paging in absent pages in the physical memory from the logical memory, or much worse, from the file system, which is the hard disk drive. And so this is what happens with thrashing. Okay. Okay, so let's move to working set model. So, what is a working set? Remember that in the operating system, if a process triggers a page fault, the operating system in random chooses one free frame from the list of free frames in order to provide for that process triggering a page fault a new free frame or a new page so that it can continue with its execution. Now, the problem is the operating system chooses the free frame randomly. So what if the operating system chooses a random free frame from another process? So this triggers page fault in another process. Now, there are many ways how to suggest to the operating system which free frame to choose. One of these ways is the working set model. The working set model is actually a group of page references that are used by the process in order to execute. Um, Actually, the limit of the page references are actually 10. So, um, the working set is actually a storage of the series of 10 memory references used by the process recently at this given moment in time in order to be executed. Um, the symbol delta stands for the working set window. This is a fixed number of page references. Um, WSSI stands for working set size of a process P sub I. This is equivalent to the total number of pages referenced is in the most recent working set window, and this varies in time. If delta is too small, then delta will not encompass entire locality. If delta or the working set window is too large, then it will encompass several localities. If working set window is equivalent to infinity, then it implies that working set window will encompass the entire program. The summation of the working set sizes of all processes in the random access memory is indicated or denoted by the letter D. So this is equivalent to the total demand frames. Total demand frames approximation of locality. So in this case, if the total or if the summation of the working set size of all processes is greater than m, which is the total number of memory sizes in the random access memory, then thrashing happens. So the policy here is if D is greater than M, then the operating system has to terminate or swap out one entire process from the random access memory in order to continue with the execution. In this case, the degree of multiprogramming is continued just by taking one process off of the random access memory. Another is how does a working set keep track of its memory references? This happens when so in order for the operating system to keep track of the working set, the operating system approximates with interval timer plus reference bit. The interval timer is actually a series of bits. In this example, it is comprised with 2 bits in order to indicate that the interval is within 1 to 5,000, 5,001 to 10,000, and 10,001 to 15,000, or 15,001 until 20,000. So the operating system, by the help of the interval timer, can know which interval a reference page belongs to. So when was the page referenced? So was it referenced during the interval from 1 to 5,000, or from 5,001 to 10,000, and so on and so forth? And another is there is a reference bit which indicates that the page is actually either or whether the page is written or not. If the reference bit is set to 1, then it was modified or written. If it was set to 0, then it is not modified. So if the timer interrupts after every 5,000 time units, what the operating system does is it keeps in memory 2 bits for each page. Whenever a timer interrupts, copy and sets the values of all reference bits to 0. If one of the bits in the memory is equal to 1, meaning it was referenced in the intervals, or it was modified by some process, then that reference has to be recorded in the working set window. Why is this important? Because in this way, by way of the working set, then the operating system would know that all memory references that are included in the working set window will no longer be chosen in order to will no longer be chosen as a free frame for a process that triggers page fault. So in this way, this process which owns the working set will not lose free frames for its execution. Now, it says here, why is this not completely accurate? Because we are just using 2 bits for the interval timer. So the improvement for this is, why not use 10 bits and interrupt every 1000 time units instead of just interrupting at every 5000 time units? So the more you increase the number of bits, the lesser time units, the more accurate your working set would be. Okay, so let's move to the page fault frequency. What is a page fault frequency? A page fault frequency is the rate of page fault of every process in the random access memory. The cause of the page fault is when there is not enough free frames or pages in the random access memory for the process to be executed. Now look at this graph. This is a visualization of collected data. If you increase the number of frames, this means that there is a decrease in the page fault rate. Now, if there is a lack of number of frames, then there is an increase of page fault rate. Now, the operating system suggests that, or rather, the page fault frequency suggests that if the operating system senses that the decrease in the number of free frames is actually at the upper bound, then there has to be an increased number of frames. If the operating system senses that the number of free frames is actually at the lower bound, then there has to be a decreased number of frames. So in this way, there will be a proper use of the list of free frames in the random access memory for every process. And also another about page fault frequency. If actual rate is too low, then the process loses frame. If actual rate is too high, then the process gains frame. So this is some sort of a rule of thumb for the page fault frequency. Another for this one, this is a graph in relation with working sets. No, this is a graph about working sets and page fault rates. So right at this part, there is actually a peak with respect to the page fault rate. This means that the operating system is paging in necessary pages for the process to execute properly. Now, there is a depression right here, a plateau, which means that every active pages necessary for the process to be executed are already in the random access memory. So in this way, there will be no page fault rates. No, page fault rates will no longer be increasing because every pages necessary for the process to be executed are already stored in the random access memory. And also, this part, until this part, is actually where the working set window collects the memory references for every process to execute properly. So this is where the working set window are being composed. Okay, let's move to memory map files. Memory map file is actually a way of an operating system to access data from a file stored in a hard disk. So, um, the normal way is really by way of a standard system call, such as read or write functions. The standard system call do not allow the memory access or do not allow the file to be memory mapped by way of the random access memory. So in this way, it takes a very slow process execution compared with memory mapped files. So memory map file is actually memory map file I/O allows file I/O to be treated as routine memory access by mapping a disk block to a page in memory. So a file is initially read using demand paging. Um, a page size portion of the file is read from the file system into a physical page. Remember that a physical page is located in the random access memory. A page size portion of the file is coming from the file system, which is located in the hard disk drive. Another is in memory map files, subsequent reads, writes to, from the file are treated as ordinary memory accesses. This makes the memory map files contribute to the fast process execution compared with standard system calls. Another is memory map files simplify and speed file access by driving file I/O through memory rather than read and write system calls. So in this way, because memory mapping or memory map file memory map file system calls are faster than standard system calls such as read and write functions, then there is a fast process execution. Also, memory map files allow several processes to map the same file, allowing the pages in memory to be shared. So there is a sharing of memory map files in the random access memory for multiple processes. So in this part, copy on write can actually be implemented here. Why? Because if a memory map file is being read by multiple processes, there is no need for copying or making a copy for every process. But if the operation done is actually a writing of data into the memory map file, then the process is actually modifying the data of that memory map file. And so there has to be a need for creating a copy of that memory map file so that that copy can be edited by that process so that synchronization problem can be avoided. But the point is, or the question is, when will the operating system need to write the data back into the hard disk drive? This is when the close system call function is invoked by the process. So when this system call is invoked, then all the modified data in that memory map file will be written back to the hard disk drive. Next, let's move to the next slide. So this one, memory map file technique for all I/O. Some operating systems use memory map files for standard I/O. Process can explicitly request memory mapping a file via mmap system call. This is apart from a standard system call. which is open, read, write, and close functions. An mmap is actually a special um, system call. What it does is it puts the memory map file in the user address space instead of putting it in the standard, or rather in the kernel address space, as is done by system calls, standard system calls. So now file mapped into process address space or user address space. For standard system calls like open, read, write, and close, such as this one, uh, mmap anyway, so meaning the operation for the mmap will be performed by some operating systems, even though the system call invoked by the process are actually standard system calls. Um, uh, Even if the standard system calls are invoked, still the operating system maps file into kernel address space, and the process still does read and write, copies data to and from kernel space and user space. So this uses efficient memory management subsystem. Why? Because the memory management subsystem is located in the kernel address space of the monolithic operating system. It is not run in the random access memory part of the user address space. So this avoids the need of implementing a separate memory management subsystem. And as I have said earlier, copy on write, or COW, is implemented because of the sharing of memory map file for reading and writing non-shared pages. Another is memory map files can be used for shared memory, although again via separate system calls. So let's move to the next slide. Memory map files. Now this is a diagram that shows how memory map files are implemented. So basically, the memory map file are located in the random access memory coming from the disk file. And these memory map files are all shared by two processes, process A and process B. So that's how you implement a memory map files by allowing multiple processes to participate in it. Next, another is this one. So this is shared memory via memory mapped I/O. So a part of the random access memory where the memory map file is located is actually shared by two processes, process 1 and process 2. So they have a copy of that shared memory in their process control blocks. So that's it for the memory map files. Okay, let's proceed to shared memory in Windows API. The operating system, especially Windows operating system, allows the development of computer programs that can actually share memory um, memory mapped files in using random access memory. So let's consider the producer consumer problem. In the producer, there is a computer program. Within the computer program of the producer, there is a line that says create file, which results with a handle to that file. And then there is a line there that says create file mapping. The create file mapping function actually creates a memory shared named shared memory object that can be shared by the producer computer program together with the consumer computer program. And before this named shared memory object be shared, there has to be a view of this file. So there is map view of file function. And um, in addition to this, this is for the computer program under the producer. What about the computer program under the uh, consumer? The consumer will have to open a file in order to have a handle of the file created by the producer computer program. And instead of writing a create file mapping function, the named shared memory object will be uh, presented as one of the parameters in the create in the open file function. And the consumer computer program will create um, a view of that file shared with the consumer by the producer computer program by way of map view of file function. Okay, let's move to allocating kernel memory. As we all know, every time a process that is uh, stored in the user address space um, requires a free frame or a page, um, then the operating system will allocate free frames from the list of free frames located in the user address space part of the random access memory. But if the user process is actually located in the kernel address space, the operating system will allocate a free frame from the list of free frames, not from the user address space, but from the kernel address space. So this is our next topic now. Allocating kernel memory is treated differently from user memory. Often allocated from a free memory pool, kernel requests memory for structures of varying sizes. And also, some kernel memory needs to be contiguous, that is, for device I/O. Um, as we all know, processes are composed of program structures and data structures. When we speak about data structures, there are varying sizes for every specific data structure. And um, some kernel memory needs need to be contiguous. So the free frame allocation of the operating system to that process must be in contiguous arrangement, especially for device I/O or I/O devices. And so um, the system, the paging system for user processes cannot be used for as the paging system for processes in the kernel address space. So next is we move to the two, or rather the four um, means in order to solve the problem of allocating free frames from fragmented or separate locations in the random access memory, because some kernel processes require that there has to be uh, a contiguous arrangement of memory or frames that will be allocated to every kernel process. So the first method, or the first solution for this, is the buddy system. The buddy system is actually a way of allocating memory from fixed size segment consisting of physically contiguous pages. So the size of these physically contiguous pages are by the power of 2. This means that they grow by a factor of 2. No? Um, this satisfies requests in unit size as power of 2. This requests rounded up to the next highest power of 2. And when smaller allocation needed than is available, current chunks split into two bodies of next lower power of 2. Continue until appropriate sized chunk available. So, say for example, the operating system needs to allocate a free frame that is small to a kernel process, then the pages are going to be divided enough to contain that small need for memory. If the operating system requires to allocate larger pages to a process, no, to a kernel process, then the pages will be multiplied by a power of 2 in order to have enough memory for that memory need of that kernel process. In this way, no, the consequence of this is there is a higher chance of having fragmented um, or fragmentation in the random access memory. For example, assume 256 kilobytes chunk, 256 kilobyte chunk available in the random access memory, and the kernel requests for 21 kilobytes. So the 256 kilobyte page must be split into 128 kilobytes and then further divided into 64 kilobytes. So one further um, division so that it can become 32 kilobytes, which is the one that will satisfy the request for a 21 kilobyte page. The advantage of this is that every time there is a need for a greater size of memory, then a coalesce can happen, such as what is mentioned here, meaning the body system can provide a greater size of memory by multiplying by a power of 2, no? Multiplying by a factor of 2, so that the operating system can satisfy the need of the process. The disadvantage of this body system is really the fragmentation, because no matter how much you divide, there is always a space that is empty that is allocated to a process. Another, this is the diagram for the body system. So a 256 kilobyte page will be divided into 228 kilobytes, and one 128 kilobyte page will be subdivided into 64 kilobytes, two of these, and then 164 kilobyte page will be subdivided into two smaller 32 kilobyte pages. Another is other than the body system, we have the slab allocator. The slab allocator is actually another alternate strategy. So slab is one or more physically contiguous pages. So let's move to the next slide. This one. A slab is actually combined in order to produce caches. And one slab is where a kernel object resides. So if we move to the previous slide, and let's discuss this one by one. A slab is one or more physically contiguous pages. A cache consists of one or more, or is consisted of one or more slabs. A single cache for each unique kernel data structure. Each cache filled with objects, instantiations of the data structure. So meaning there are already predefined objects of the given sizes for every slab. So every time the process asks the operating system for more memory references, then the slab allocator will contribute to the fast process execution, because there are already pre-created objects in the memory that can be allocated at a very fast way or very fast rate. When cache created filled with objects marked as free, and when structures stored objects marked as used, if slab is full of used objects, next object allocated from empty slab If no empty slabs, new slab allocated. So this means that um, there are actually ways of how to allocate free frames or slabs to a process. So first, the operating system will look for a slab that is partially used. If there is no pages that are partially used, then it will look for free slabs that are not used by the operating system, or rather not used by the process at for us for the meantime. So that specific slab will be allocated for the process that is being executed in the memory. So the benefits include, no, in using slab allocation is really there is very little chance of having fragmentation, as slab allocators have varying sizes compared with the body system. So if the body system has a greater space, no, empty space in their pages, slab allocators, if there is uh, such a thing as an empty space in its slab, that size of that empty space inside the slab is definitely smaller than the size of the empty space in the body system. So um, the good thing about slab allocation is that it can promote less fragmentation, if not no fragmentation at all. Another is, I have discussed earlier that a slab allocator um, categorizes three of its slabs. One is for full, when a slab is fully used by a process; empty, if the slab is free and if not used by any process; and partial, if the slab is composed of a part that is used by a process and a part that is free of any process. So, upon request, the slab allocator uses free struct in partial slab, given that uh, the process is actually asking for a slab for the task struct data structure. So in this case, um, the slab allocator uses free struct in partial slab. If there is none, then the slab allocator takes one from empty slab, and if no empty slab is available, then the slab allocator creates a new empty slab for this request of the process for further memory references. Another is the slab allocator in uh, Linux is actually implemented by the Solaris operating system, now widespread for both kernel mode and user memory in various OSes. Linux 2.2 had slab, now has both slob and slub allocators. Slab, by the way, is short for simple list of blocks. Um, Slob maintains three list objects for small, medium, and large objects. So this means that slob uh, is different from slab allocator because a slob can actually provide less fragmentation compared with the slab allocator. But there is a new one. This is called slub, which is performance optimized slab, which removes per CPU queues metadata stored in page structure. So this means that the size of the slab in the slab allocator are actually minimized because the per CPU queues are removed, and the metadata stored in every slab are also removed. So this means that the slab allocator has a very small size slab compared with the previous slab allocator. So this also adds up to the decrease of fragmentation or waste of memory spaces or memory references in the random access memory. Okay, so we move to pre-paging. Pre-paging helps if the process that is being executed by the processor has many page faults in it. So pre-paging all the pages, the active pages necessary to execute the process will lessen the future page fault rates of this given process. We are given a formula here. S stands for uh, the or rather S stands for pages that are pre-paged for a given process. Alpha stands for the pages that are used by the processor for executing this process. Now the product of S and alpha signifies the used or active pages used in executing the process. Now, if S times alpha is greater than or less than the cost of pre-paging, we will know this if we use the formula S times 1 minus alpha. 1 minus alpha indicates the amount of pages that are not used in executing the process. You multiply that with S and then you get the number of pages that are not used in executing the process. Now, if the alpha is near 0, this means that the alpha or the number of pages used are actually very few. So pre-paging loses, no? To pre-page pages necessary for the process to execute is actually contributing to the slow process execution of the process executed by the processor. But if the alpha, the value of alpha is actually greater than 0, this means that pre-paging will add up to fast process execution of the process executed by the processor. Okay, let's move to page sizes. Um, a page size is actually the literal size of the page stored in the logical memory or logical address. I mean, logical memory. Now, what happens if we increase the page size? We have a series of parameters here, such as fragmentation, page table size, resolution, I/O overhead, number of page faults, locality, and translation look-aside buffer size and effectiveness. So, first, what will happen in page size? Sometimes, some operating system designers have a choice, especially if running on custom-built CPU. If you increase the page size, then the fragmentation will increase because there are times when the instruction necessary for the process to be executed are actually just a small space in that page that is being paged in. So increase in page size increases the rate of fragmentation. Another is page table size. When you increase the page size, then the page table size of every process will grow in size, no? Directly proportional to the page size. When the page size increase, there will be, I think, a positive correlation with the page table size. Another is the resolution. A resolution is actually uh, the number of fragmentation, or rather, how much small page can be stored in the random access memory. If you have a very large page size, then this decreases the number of resolution or the number of pages to be stored in the random access memory. If you decrease the page size, then the resolution will have a greater chance of inserting smaller sized pages into the random access memory. When you increase the page size, the I/O overhead will lessen because the I/O overhead means that how much transfer time is necessary for a page size to be transferred from the hard disk drive or the logical memory to the physical memory. So, based on the book, if there is a great page size involved, the I/O overhead is very minimal. But if you multiply the page size with 2, then the I/O overhead is great. So when you increase the page size, then the I/O overhead will not exponentially increase. But if you double the page size or triple the page size, then the I/O overhead will increase exponentially. Another is when you increase the page size, it will lessen the number of page faults because the necessary instructions for the process to be executed are usually located within those pages. If you decrease the number of page size, then the number of page faults will also increase. What happens if you increase the page size with locality? If you increase the number of page size, then the locality will increase because every page or every program structure and data structure are already inside the page that is being transferred, no? Within that great sized page size or within that page size. When you decrease the page size, then the locality will suffer because the instructions necessary for the process to be executed might be stored in another page. So this means that that page has the possibility of being stored in a different memory reference. So locality will suffer. If you increase the page size, what happens with the translation look-aside buffer size and effectiveness? If there is a if there is a great size with respect to page size in the random access memory, then if you have a great TLB size, then there is a greater chance of hitting all the memory references in the random access memory because the greater the page size, the smaller the number of free frames in the random access memory. But if there is a smaller page size, then this means that there is an increase of a number of free frames in the random access memory. And because the translation look-aside buffer is smaller than the size of the memory or the physical memory, then there will be misses if there is a mapping that is involved or search functionality. So there will be entries in the free frame that will no longer be discovered based on the data stored in the translation look-aside buffer. Another is always power of 2, usually in the range of 2 raised to the power of 12 or 4096 bytes to 2 raised to the power of 22, which is 4,194,304 bytes. So this is the usual size of the page. Another is on average growing over time. Usually this means that the page size usually grows over time, and that's the average rate of growth of a page size. Let's move to translation look-aside buffer reach. As we all know, TLB is not part of the user program or the kernel program. This is actually part of the hardware, the computer organization. It is an electronic device. Translation look-aside buffer reach, on the other hand, is really the amount of memory accessible from the translation look-aside buffer. And the equation for this is the translation look-aside buffer size multiplied with the actual page size. So this is how you calculate the translation look-aside buffer reach. Now, Why do you have to multiply the translation look-aside buffer size with the page size? This is because one page is equivalent to multiple entries, or what books call the offset. So say for example, one page size is equivalent to 8 bytes, then the size of the translation look-aside buffer has to be multiplied with the number 8 in order to calculate for the TLB reach. So it says here, ideally the working set of each process is stored in the translation look-aside buffer. Otherwise, there is a high degree of page faults. And this is very true, because if the working set is not stored in the physical memory or the translation look-aside buffer, then there will be page faults that will be triggered by every process executed by the processor. Another is, when you increase the page size, this may lead to an increase in fragmentation. Why? Because not all applications require a large page size. So when an application or a process only requires a small amount of small area of a page, and if the operating system paging system transfers a page with a great page size, then there will be fragmentation that will happen. Another is this one. Provide multiple page sizes. Now this allows the applications that require larger page sizes the opportunity to use them without an increase in fragmentation. Why? Because if the needed page size of the process is really a great size of a page, then you just combine multiple page sizes, and then you can have the necessary memory requested by that process. Even though there is an empty area among those combined multiple page sizes, it will not be as spacious as the fragmentation involved in increasing the page size. So it is minimal. Okay, let's move to the program structure. As we all know, um, a computer program or a computer process is actually composed of program structure and data structure. The program structure cannot be changed, but the data structure can actually be changed or be improved in order to contribute for the fast process execution of the current process. Now, let's consider this example. We have an array of 128 rows and 128 columns right at this point of the program. What's the difference between program 1 and program 2? In program 1, the population of the array is actually from top to bottom. In program 2, that's in program 1. This one, in program 2, the population of the array is actually from left to right. Now, which is more optimized with respect to virtual memory? Actually, the optimized one is really program 2. Why? In an array, we are actually having, say for example, a rectangular or a square shaped array. We all know that according to the book, it says that one row is actually equivalent to one page. Say for example, you have 128 elements, and every element of an integer is actually equivalent to 1 byte. Now, one line of row in an array is actually equivalent to a page. Now, consider program number 1. If program number 1 will populate the array from top to bottom, then there will be 128 page faults for that process. And because it will populate from left to right, then it will page fault 16,384 page faults just to populate the array. But compared with program number 2, which is it is populating the array from left to right, um, it's actually going to page fault one at a time because it populates one page at a time. So it contributes to the fast process execution if you do your populating using this method of programming. Okay, let's move to interlock. Um, it says here, IO interlock. These are pages. Pages must sometimes be locked into memory. Let's consider a situation. Say, for example, there is a process that page faults, and then the necessary page is already stored in the random access memory. What if there is another process that page faults and then requires a frame, but the operating system takes away the paged in free frame or memory um, for the previous process. Now, if the previous process that page faulted uh, is executed once again by the processor, and the necessary page or instruction uh, is not in the active pages of that process, then it will page fault once again. So there is a need for locking. This is what interlock is all about. No, there's a need for locking memory or pages in the random access memory together with a specific process so that the operating system will not choose it for uh, a free frame to be used by another process. So it says here, um, consider I/O. Pages that are used for copying a file from a device must be locked from being selected for eviction by a page replacement algorithm. The purpose of this is so that the previous process might make use of the paged in uh, instruction from the hard disk drive to the random access memory so that it can be used by the process itself. Another term that is used here is pinning. Pinning of pages to lock into memory. One example of this, as stated in the book by Silberschatz's, is actually a database computer program. Most of the time, a database computer program locks a memory uh, space, no, memory reference, together with the process, no, the database program, because the database program figures that it can wisely manage the memory space better than the operating system. So, in order to implement the interlocking or the pinning, there has to be a lock bit that is incorporated with every page, just so that page, when the lock bit is set, can be used by that specific process and not be used by another process due to page replacement algorithm. Okay, for the Windows operating system, by the way, we are discussing some of the operating systems, one Windows and second Solaris. The first operating system is Windows operating system. Um, Whenever the Windows operating system populates the random access memory, every process actually assigned with a number of pages. The first number of pages is really the working set minimum. The working set minimum is the number of pages allowed for a given process. The working set maximum is the maximum number of pages allowed for a process. Say for example, a process page faults, but the number of pages under that process is not exceeding the working set maximum yet. So what the Windows operating system does is it borrows a free frame from the list of free frames and then assign that to the process page faulting. And so the process can continue its execution. But when the process page faults, and then the number of pages in the process is actually equal to the working set maximum, the Windows operating system will not borrow a free frame from the list of free frames, but it will have to uh, command or allow the process to let go of one of the pages in its address space so that that free frame can be recycled by that same process. Uh, what happens if there's actually a value called threshold? A threshold is actually a value, a number of sufficient memory references, or a number of list of a number of free frames in the random access memory. When the threshold value is actually below its normal value, then the Windows operating system does an automatic working set trimming. So it will collect all the free frames, no, all the pages from the processes that are actually moving or having a number of pages more than its working set minimum. And all of the pages collected will be incorporated together with a list of free frames in the random access memory. Um, it says here, working set trimming removes pages from processes that have pages in excess of their working set minimum. So that's it for Windows operating system. Okay, so after Windows operating system, we discuss about Solaris operating system, how the page replacement algorithm is done by the Solaris operating system. In the Solaris operating system, if there is a page fault, there is actually a function called page out, which scans the pages owned by different processes in order to make sure that there is enough free frames in the list of free frames owned by the operating system. We have a series of values. First one, this is the lots free. Lots free is actually uh, the threshold parameter or value where the Solaris operating system begins to page out. The second is the des-free, or the threshold parameter to increasing paging. So if page out function begins at lots free, no, if the number of free pages, or rather, if the number of free pages moves below lots free, then the Solaris operating system begins to page out. If the number of free pages moves below des-free threshold parameter, then Solaris operating system increases its page out. If the number of free pages moves below min free, then every time there is a page fault, there has to be a page out afterwards. Paging is performed by, as I have said, page out process. And page out scans pages using modified clock algorithm. So, because it is a modified clock algorithm, it actually implements two clock hands. The first clock scans the pages of every process in order to set all reference bits to 0. And the second hand scans the pages owned by every process so that if the reference bit is set to 1, then it will be, or the data will be written back to the hard disk drive, and then the free frame will be recycled. And if the reference bit is not set to 1, then it will just be recycled or incorporated together with the list of free frames. Another, it says here, scan rate is the rate at which pages are scanned. This ranges from slow scan to fast scan. This means that if it is slow scan, then it will scan uh, the remaining processes at around 100 pages per second. But if it is a fast scan, then it will scan the remaining pages at 8,192 pages per second. So the move from slow scan to fast scan depends upon the value of the number of pages in the list of free frames. If it's slots free, then it's slow scan. If it's des free, then it's in the middle of slow scan and fast scan. If it's min free or below min free, then it's supposed to be the fast scan. Page out is called more frequently depending upon the amount of free memory available. So it says here, page out is called more frequently depending upon the amount of free memory available. Let's move to the next slide. The next slide has something to do with a graph, this one. So as you can see right here, if there is a small amount of free memory, then a fast scan has to be implemented. If if the amount of memory is right in the middle, then there has to be in between slow scan and fast scan rate. And if it is slots free, meaning if there are a lot of amount of free memory, then a slow scan has to be performed because there's no need for fast scan anyway, because there's a lot of free frames available in the random access memory. Okay, so that wraps up. That's it for the my part of the reporting, my part of virtual memory. So on behalf of Miss Alce, I'm thanking all of you for listening to my reporting. Thank you very much, and have a good day. God bless.